Okay, so we fixed that. Well, good morning, everyone. And I'm happy to be here to kind of a quick recap of our hands-on sessions. And so for those of you that didn't take part, we were trying to focus on giving some intuition about the spectroscopy of young planets and their thermal evolution and what are the things that an observer might go look for. The modeling underlying this, the atmosphere models, the evolution models, all come from my group, and all the tools, 99% of everything you touched your hands to was all created from the amazing Natasha Batala, who put together Picasso and interfaced it with the models. So really, we need a big sign of support for Natasha, who is getting married tomorrow. So she did all of this while also planning a wedding. And much less importantly, I also this week unexpectedly we are trying to buy a house in Tucson, and it came to fruition. And we had to make an unexpected trip to Tucson earlier this week. So I've been distracted more than I would like to have been for this. So I want to thank Elise, who helped me put together these slides for the summary and pull things together. So with that said, I also want to thank all of our breakout helpers who helped yesterday. They were facilitated this, and we got lots of great feedback on how people enjoyed working with them. So I really want to thank all of our facilitators. So the big picture that we sort of framed all of this around is this idea that core accretion planets are born differently than companion objects like brown dwarf companions. And so can we tell the difference between core accretion and other formation models by looking at the characteristics of young planets? And the idea is that core accreted models form smaller, colder, and with lower luminosity, as you see on the right. And the difference in these cases is really sort of two extremes, and nature probably in reality produces a more of a range of possibilities. But this is a good place to start to think about what the challenges are in trying to tease out formation. And so we started the exercise with having you look at planet evolution tracks, which for ease of use, we call the cold start and the hot start models. And you see that cold start models start colder because they've radiated away a lot of their initial potential energy in an accretion shock. And so if you pick a given mass at a fixed age, the core accreted models have a very different spectra than the hot start models, as you see on the right. But all of this, both the evolution and the spectra, are connected by atmosphere models, which give the run of temperature and pressure through the atmosphere. And so the atmosphere controls everything. It controls the evolution by controlling how fast the planets cool once they're formed, and also by controlling their spectra. And so you need some model to start doing any of this, the evolution or the spectroscopy. What we did for this exercise was provide everyone with our own set of models, which we call the Sonora models, that were pre-calculated and are available online. Of course, you could go and produce your own model or change the temperature profile as you see fit, but for this exercise, we just started with those. And so this was the overall overview on what we were hoping that you could understand is, given different sets of models, can you tease out the formation? And as in breakout room 1 slide from Jennifer Greco leading, the first thing, of course, is that planets that form through cold accretion start off much colder. And what that means, if you look at the right, is the atmospheric chemistry is different. So for a given planet, at say 10 million years, a 2 Jupiter mass planet at 10 million years, in the hot start case, it's still very warm, temperature well above 1,000 degrees. And so that gives you carbon monoxide instead of methane. And at colder temperatures, below effective temperatures of about 1,000, you get methane dominates over carbon monoxide. So one of the first things you could look at is to see what you're dealing with is what's going on with the atmospheric carbon species. And this was, I think everybody got this in breakout room 8. Louise Nielsen also found these type of things. And if you look carefully at the cases, there's also differences in things like ammonia, which is and molecular nitrogen, which is harder to tease out just in the near infrared. But with JWST data, ammonia, even in these hotter cases, is a very clear species. So then after this overview, the next question is, how do we start dissecting the spectra? And what are the things that we look for, and where do we expect to start seeing these different species? And also I want to comment, my overview here is going to be pretty quick. If you have any questions, put them in the Q&A and I'll answer them at the end. So go ahead and feel free to type in questions if you had questions, unresolved questions from the breakout rooms. And so here we see a cold start model and a hot start model, and again, the species. That slide's out of order. But once you have the species, you can start looking at the spectra. And Natasha's written a really great tool that allows you to look as a function of wavelength for a given model to see what at any given wavelength the main contributors to the opacity are. And this is really helpful if you're trying to detect any particular species. For example, okay, we want to detect carbon monoxide. Where can we go detect carbon monoxide? And if you look at the bottom right panel for the hot start, most of the continuum there is from water, H2O in the green line, but CO starts to poke up around 2.5 microns. Whereas in the cold start case up higher, the green line is now methane and water's in yellow, but you can see that methane competes with and exceeds water in the importance of its optical depth. And you can also see that at other wavelengths, other molecules start to pop up, like CO at 4.5 microns starts to compete with water. And so if you did want to see small amounts of carbon monoxide, 4.5 to 5 microns would be a great place to look. And so there's lots of intuition you can build by looking at plots like these. And we really wanted you to learn how to use the tool to get a feeling for how to do this. You can also think, once you understand what species you're seeing, you can also take a model spectrum and plot it along with blackbody curves. And in this portion of the exercise, we had you plot some blackbody curves along with the model spectra, and you can start to tease out how deep in the atmosphere you're looking. And this is really a key thing for all of these atmospheres. I like to think of it as you're looking down from the top, like looking down at the ocean, someplace it's like Big Sur in California, where the water is really clear and you can see 10 or 20 feet down, or other places like in Greece, where you can see to beautiful depths. And for some of these models where the atmospheric capacity is very low, you can see quite deep. And when you see deep, because the atmosphere gets warmer as you go deeper, the atmosphere is hotter, and so the flux is emerging from higher temperatures, and that gives you these spectral peaks like you see in the top panel in the cold start models. And so regions where the spectrum is not as bright, you're looking higher up in the atmosphere where it's colder. And so you can see, for example, and again in the cold start case, the dynamic range you're looking through is, say, in J band, you're looking at 10 bars pressure, 1500 Kelvin, whereas in the depths of the water bands or the methane bands, you're looking higher up in the atmosphere where it's cooler. And even at 3.3 microns, you barely can't see it. That yellow line is higher up at 0.1 bars. And so by looking at this range and appreciating how deep you're looking in the atmosphere, you can start to get a handle on the overall atmospheric temperature pressure profile. And this is how retrievals work. Here we're trying to get you to do this in sort of a intuition building way, but atmospheric retrieval codes use exactly this characteristic of the atmospheres. They're not black bodies. You're getting information throughout the atmosphere. And so then we went on to have you look at the various differences in hot versus cold and say, well, if you didn't know the mass, how much information can you really tease out from these guys? And so here's an example from the workbook of, again, the cold and hot start models looking at luminosity versus age with a number of known companions with real data. And you can see that most of those objects are clearly hot start objects. You could not have formed them. They did not form by core accretion. But you get down to the lower portion, and that point there on the sort of in the lower left quadrant is 51 Area B. And it sits on either a cold start model that's a little bit more massive or a hot start lower mass model. So we'd really like to know, okay, this could be either one. That's exciting. Which one is it? And the luminosity, at this point, the luminosity and the radius is pretty similar between these different cases. What's really different is the gravity. So the more massive object, say, has twice the mass, the same radius, so it has about twice the gravity. And if we didn't have any other measures of the mass, there's no radial velocity because they're young stars, it's hard to do. We don't have astrometry yet. Maybe Gaia will get it for us. But right now, we don't know anything. So can we tell just from the spectra? And we have here, for example, in a case that Natasha picked out where it's pretty ambiguous. In this case, she's looking at a 10 Jupiter mass cold star and a 4 Jupiter mass hot star, both at the same age, and they look an awful lot alike. And so this is another part of the exercise, was to try to give some appreciation that the spectra don't always save you. It can be very tricky to try to see the differences. The differences you see here are mostly because of different gravities in the atmosphere. And I think everybody got that. Jennifer Greco's slide from breakout room 1, I put a red box around the comment of having measurements of masses would make determining the differences easier. And that's absolutely true. If you knew the mass, if you say, oh, this is definitely a 10 Jupiter mass, then you could compare that back to the formation models. But just trying to do it from the spectra is tricky. And so once folks had that, there was a number of exercises just fleshing this out and looking at particularly different species and where would you go to look at different species. Louise Nielsen's from breakout room 8 also came to the same conclusion. You really need to have the masses. But even if you did, there's also issues of the unknowns in the models. And what about clouds, for example, and how could clouds impact the spectra? And on the right is a plot that this group put together of the difference in the difference in the spectra with and without clouds, and for various different models. And you can see there's a lot of, there's up to 100% differences. There's huge differences when you account for clouds. And so we except for the sort of the optional book 3, which looked at the clouds, we ignored those. And these were all much easier to do with clear atmospheres. And also Laura Mayorga from breakout room 2 also came to this conclusion about how clouds can be difficult. Again, this is the optical depth plot on the top, on the left, and they've drawn in a little cloud. And if you did have a high cloud, as I said on Wednesday, the clouds tend to smooth out the spectral features. They heat up the upper atmosphere. They don't let you see as deep. It's like, back to the ocean analogy, all of a sudden a bunch of silt's flown in and you really can't see much below the surface of the water because you're just looking at the silt in the water, and the clouds are kind of like that. And again, this group spent some time looking at the different spectral features and called out 5 microns is a good place to look for CO. And I do think that with JWST, we start getting spectra of these objects, really be able to characterize how much the CO abundance in band is going to be really helpful. Of course, a problem we didn't even touch is disequilibrium chemistry, which tends to enhance the CO and depress the methane in these transitional objects around 1,700 Kelvin. And so again, just like with clouds, you have chemistry, which is another difficulty. So, in conclusion, the models which we connect the formation, the evolution, the thermal profile, the spectra, and you can use online repositories. I hope you have some confidence now that you can do that. For example, the Sonora Models, but there's plenty of other brands of models, and it's always important to try different model sets to see how much the conclusions vary because of the different assumptions the different modeling groups made. And tools, and Picasso is nice because it's open source, and it does both, it does transmission, reflection, and thermal emission. So it's very flexible, and you can then, it allows you to produce spectra, not just taking the spectra from the repositories. For example, the Sonora Models have both temperature profiles and the spectra online, but now you can take these and change the assumptions. You could change the methane abundance, or you could change the carbon monoxide abundance and see how that impacts the spectra. But the bottom line we hope you got out of it is there's really complex interplays between all of these different inputs to the models: mass, gravity, atmospheric temperature, clouds, dynamics. And it's not always easy if you have two planets about the same temperature and maybe just different gravity, especially for differences like factors of 2, it's not easy to tell them apart. And so teasing out these individual characteristics is challenging, and it would be really helpful to have additional information such as mass to help with this. So the bottom line is we hope you've enjoyed learning about these resources and have built some intuition. And stand by from our group. We have many more models that will be coming shortly. We have a whole set of disequilibrium chemistry models we'll be posting online soon, and we're calling those Sonora Choya. And we're working our way through the alphabet of desert species of the American Southwest. So with that said, let me take a look. And there's a couple of questions in the Q&A since I finished fast. Do you think having higher spectra, higher resolution spectra would allow us to make better determinations of the evolutionary paths on account of better constraints on species that exist at a specific epoch? Might have been nice to be able to change the resolutions around a bit more. Yes, and I think there was a talk on the high resolution spectra yesterday, and just for the mechanics of this, we gave you the opacities at a fixed spectral resolution, but you can download higher spectral resolutions. You can look at cross correlation methods are becoming very popular and are very powerful for teasing out. My dog's starting to make some noise. I apologize. Higher resolution spectra allow you to recognize things you might not otherwise recognize by doing cross correlation analysis. I'm going to move my dog. I'll be back in 30 seconds. My apologies. I have a 17-year-old dog, and sometimes he can't stand up, and then he cries like a baby, and it's challenging. So yes, high resolution is good, and yes, you can download online high resolution opacities, and we're going to be posting higher resolution models as well in the future. Question asked about the sodium appearance for determining the formation model. Certainly, the sodium and potassium are important species because they condense out of the atmosphere and they have a big impact. And those are another indicator of atmospheric temperature. But again, you can run into questions of, what are the clouds doing? And we've completely ignored the higher temperature clouds, which complicate things. But the sodium and potassium are also, just like with methane, can be indicators. There's, again, distress. There's never going to be one magic indicator for the formation. Let's see. Can lower wavelength data help us determining which had hot one and which had a cold star? So again, the more spectra you have, the better you can do at the more of spectral range that you have, the more species you can get together and start to make a case systematically for what you have. If you look, we didn't really stress too much about the available online data. The available data for the directly imaged planets, but it typically is not really great signal to noise ratio and typically not very high spectral resolution. There is, however, for example, for the HR 8799 planets, Quinn Konopacki and others have done great work with OSIRIS spectra, getting very high resolution and starting to tease out individual, they've done that, some time ago, teasing out individual molecular detections. But a lot of times with the cross correlation, you don't get the abundances. You detect the molecule, but not always exactly how much you have. And then really, Mark Booth asked, how much of an impact do evolutionary effects after formation, accretion of planetesimals have on the spectra, i.e. does that stop us from being able to distinguish from hot and cold star? And I think that's really important, is what's happening. Do we have higher, Jupiter and Saturn have enhanced metallicity over the sun? Is that being delivered by late arriving planetesimals that are giving us higher metallicity? And maybe that's an important thing to look at. These late accreting planetesimals, if you think of the SL9 impacts on Jupiter, produce clouds, high altitude dust layers. And if we have an accreting planet, do we have a lot of pollution in the atmosphere that would also complicate what we're trying to see? And maybe we're mistaking what we think is a cloud layer and is actually something coming in from the outside. And we've touched on that in some recent papers, and other groups have too, is the impact of the pollution on these spectra. Let's see. Can knowing the spatial position of the planet give you any insight into the age and evolutionary stage? And certainly the efforts to understand the orbits with the HR 8799 planets, orbital stability arguments place constraints on the masses. They can't be too massive, or else they wouldn't have lasted in their current orbits to their age. And that's really helpful, because when you try to fit models for those planets, you do in fact have some upper limits on what the masses can be, and that helps constrain the atmospheric models. So is my dog a good boy? He very much is. And I think I'm going to pause there. There's a question on optical depth that's maybe better answered in text. And I think the next talk is a little bit long, so I'm going to stop a little bit short here. And so I want to thank everyone for taking part in these exercises. We hope you've built up some new skills and have some more confidence in downloading the Spectra models, evolution models, and playing around with them yourself. And so I'll end it there.